In this video, we're going to be looking at some of the quantitative and qualitative relationships between gas parameters. We call these collectively the gas laws. And so we're going to start here with a rather simple one you've probably encountered. It's called Boyles Law. Now, the concept of Boyles Law is simple. It says that the pressure and volume of a gas are inversely proportional. There is a little bit of a proviso on this that we do need to be careful about. And that proviso is they are inversely proportional at constant temperature and amount of gas. So if I have a balloon that I'm holding at a constant temperature and I've tied off the balloon so that no gas can go in or out, then Boyle's law definitely applies. Pressure and volume are inversely proportional. If I push on the balloon and try to make the balloon smaller, I'm going to feel a massive increase in the pressure inside pushing out against me. And vice versa. If I stretch that balloon, if I try and make the balloon bigger somehow, the internal pressure inside the balloon is going to be considerably less. Now, mathematically speaking, pay attention to the language here and how it relates to the equation itself. When we see the term inversely proportional, what that's going to mean is that our parameters are going to be multiplied by each other. And so inverse relationships lead to multiplications in our equations. And so the pressure times the volume of a gas at one set of conditions is going to equal to the pressure and the volume multiplied by each other at another set of conditions. Now, the other way that we can look at this is from the standpoint of kinetic molecular theory. And with kinetic molecular theory, again, we had those assumptions that we made. And what we can say with relation to that theory is that if we shrink down the volume of the box, so let's say that our container was this big, but now it's only this big. Well, inside of this bigger container, the gas molecules are moving around, but because there's so much more space, they're not going to collide with the walls of this container nearly as often as they would in this container, which is considerably smaller. Smaller space, more confined area, more collisions are going to occur. More collisions means greater pressure. So that's Boyle's law from kind of a theoretical perspective. Let's take a look at a problem involving Boyle's law. So we're told that we have a balloon filled with carbon dioxide to a pressure of 1.85 atmospheres and a volume of 1.54 liters. If temperature is constant, what is the final volume when the pressure is increased to 2.5 atmospheres? So we can see here we've got one set of conditions. So we're just going to mark that with a 1. And we've got a second set of conditions here where we don't know its final volume. This is a perfect place for Boyle's law because, again, temperature is being held constant. So P1V1 is equal to P2V2. And we can see that my pressure initially was 1.85 atmospheres multiplied by my 1.54 liters of volume. And my second pressure is 2.50 atmospheres times V2, which we're trying to find. So to get this set up properly, I'm going to have to divide both sides by 2.50 atmospheres. That will get the 2.50 to cancel on the left hand or right hand side rather, and atmospheres to cancel on the right hand side, or excuse me, the left hand side. Now I set up and I do my calculation. I got my calculator out here, 1.85 multiplied by 1.54 divided by 2.50 to 3 significant figures. I get 1.14 liters. So 1.14 liters is my secondary volume. And that makes sense, right? We have increased the pressure, so we must have seen a decrease in volume. And sure enough, we went from 1.54 to 1.14 liters. So that makes sense. Let's take a look at another gas law, another relationship. This one's called Charles' Law. Now, Charles' Law tells us that the absolute temperature and volume of a gas are directly proportional. And again, there's a proviso here. There's a caveat. At constant pressure, and again, amount of gas also held constant. The other thing that we need to look at here is it's talking about absolute temperature. Absolute temperature means we have to use degrees Kelvin. I can't use Celsius or Fahrenheit here. I have to use Kelvin. Now, these are directly proportional quantities. And again, that should make sense to you. If you think about a hot air balloon, you see an expansion of gas because of the heating of that gas. And so that causes the hot air balloon to inflate and to become larger. And that is ultimately what causes the air inside to become more buoyant, and the hot air balloon goes up in the air. So another thing to look at here, we see that we have a direct proportionality here. Direct proportionalities lead to division ratios of variables instead of products of variables. So my volume divided by my temperature at one set of conditions is equal to my volume divided by my temperature at a second set of conditions. And taking this back to kinetic molecular theory, again, it should make sense. We're increasing the temperature of the gas particles are moving faster, they're going to collide more frequently with the container wall, and that's going to cause the walls of the container to expand to account for that extra energy. Let's take a look at this from another concept. So thus far, we've held constant the idea of the amount of gas. What if we no longer did that? To do that, we would have to look at something called Avogadro's law. Avogadro's law says that the volume of gas is directly proportional to the amount of gas that is in that container. So what we have there, again, direct proportionality, we see division. Volume divided by moles on each side of the equation. Now, there's a lot of cool things about Avogadro's law. Avogadro's law tells us that it doesn't matter what the gas is, the volume of the gas is directly related to the number of moles of gas that are there. And that's a really cool kind of phenomenon. But what we can also look at is if we have similar kinds of conditions, Avogadro's law sets up for us a really common kind of idea, and that is at a specific temperature and pressure. We call it standard temperature and pressure. STP is 760 millimeters of mercury, 273 Kelvin of temperature, and we can know definitively by this definition, by this law, by this ideal behavior, that 1 mole of gas, any gas, doesn't matter if it's heavy or light, if it's made out of gigantic molecules or small molecules, 1 mole of gas, regardless of type, takes up 22.4 liters of space. That's one of the real beauties of Avogadro's law. And it's kind of like what we saw with colligative properties in the previous chapter. It doesn't matter what the identity of the gas is, they all fall under this umbrella. Pretty cool. Now, all of these have required assumptions. You know, this particular one required us to have a constant pressure and temperature in order to have this proportionality, which is why STP got brought in here. Other ones have required different things being held constant. What if we didn't have things held constant? What could we do? Well, luckily, we know that all of these things are related to each other. Pressure, volume, temperature, amount of gas, they're all interrelated. And so instead of looking at each one of these individually, what we need to recognize is that each one of them is telling us that if we have things held constant, the product or the ratio of the variables leads to a constant value. And it so happens that these constant values are all kind of the same. And so if I combine these into one equation, I get a constant value as well. And so this particular equation, this one right here, we're going to come back to that one later. This is something that we'll see in another video called the ideal gas law. We're going to focus on this one here at the bottom. This is your combined gas law, or at least what is most commonly known as the combined gas law, where we have a fixed amount of gas, but the properties of temperature, volume, and pressure are all capable of changing at the same time. And this is really common because it's kind of difficult at times to hold all three of those parameters constant. But it isn't as uncommon to see all three of them changing at the same time. And we'll show so in this next example. So in this example, I have a sample of oxygen gas at 1/2 of an atmosphere, taking up 10 liters of space at 0 degrees Celsius. What is the pressure of the gas if it is at 15 liters and 25 degrees Celsius? Now, thing that we need to be aware of, obviously we've got one set of conditions here and a second set of conditions here. But before we go jumping into putting those into the combined gas law, we need to take into consideration our 25 degrees Celsius, our 0 degrees Celsius. Those are not absolute temperatures. I need to convert them into absolute temperatures first. So the 0 it becomes 273 Kelvin, the 25 becomes 298 Kelvin, and now I have something that I can work with in terms of the combined gas law. P1 times V1 over T1 is equal to P2 times V2 over T2. So plugging in my values now, pressure initially was 1/2 of an atmosphere. Initial volume was 10.0 liters. Initial temperature was 273 Kelvin. And my final pressure, I don't know. My final volume was 15.0 liters. And my final temperature was 298 Kelvin. So working a little bit of algebraic magic here, we're going to have to get P2 by itself, which means we're going to have to multiply each side by a fractional number. So take a minute and try to work that out yourselves. I'm going to come back in here with the full answer in just about 20 seconds. So go ahead and try it for yourself. And let's see where we are in a couple seconds. So you can see that by multiplying each side by 298K over 15 liters, we cancel out the right-hand side of the equation other than P2. We cancel out the Kelvin and the liters. So all we need to do is to put in the numbers 298 times 0.5 times 10.0 divided by 15.0 divided by 273, and we get a final pressure of 0.364 atmospheres. And so that in this video, we will be going over the ideal gas law. Now, as was mentioned in the previous video, the ideal gas law is born out of the combined gas law, where we are looking at every single parameter that can be used to describe a gas and recognizing that when we put these parameters in their proper context, the ratio of products leads to a constant value. And we call that constant value R, the universal gas constant. Now, the universal gas constant comes in a number of different forms, and we've talked a little bit about those already. But the most common way that we see the ideal gas law arranged is not like this, PV over NT is equal to R. We often see it rearranged into this form. PV, that is pressure times volume, is equal to nRT, that is the number of moles of the gas multiplied by this universal gas constant multiplied by the absolute temperature in degrees Kelvin. And this is going to be a really important equation for us because we can use it not so much to describe when gases are changing conditions, but rather if we know certain parameters about a gas, we can use this equation to figure out other parameters of the gas. So if I know the pressure and volume and temperature of a gas, I can use that to calculate and figure out the number of moles of gas present without actually having to measure the mass of the gas or anything like that. So really kind of important, and we'll see that this has a lot of utility in several different types of calculations. In particular, as we'll see in a future video, stoichiometry type of calculations, where we look at things that are happening in the gas phase and how they are changing over time as the reaction proceeds. Now let's talk a little bit about that universal gas constant R. Now, there are a number of different versions of the universal gas constant. In the SI system, we see it used in this way, where we have pascals or kilopascals. And the problem with these is that, again, pascals and kilopascals are ridiculously small units. But where is more commonly for us to use is if we can use our conversions between our pressure units and each other, we can take this value and put it into terms that are a lot easier for us to know. And these two values for the universal gas constant, one that uses atmospheres, 0.08206 liter atmospheres per mole K, and then this one, liters times millimeters of mercury per mole K, which we also will see torr thrown into this in place of the millimeters of mercury. These are our most common universal gas constants. And notice this part, the liters and the mole K, kind of doesn't change very much from unit to unit. And so really the value of R that we use is dictated by our pressure unit first and foremost. So let's take a look at a couple of examples of some calculations that we can do with the ideal gas law and this universal gas constant. Now the first one is actually a bit of a trick. How many moles of gas are in a 4-liter container at STP? You could use the ideal gas law to solve this problem. But if you think back to Avogadro's law, one of the very simple things that was brought out of Avogadro's law is that 1 mole of gas at STP is equal to 22.4 liters. So if I know that, and I know my Avogadro's law, I don't actually need to use the ideal gas law in this case. I can just take my 4.0 liters of gas and just do a dimensional analysis, unit conversion. 22.4 liters of gas is equal to 1 mole of gas. My liters of gas cancel. All I need to do, 4 divided by 22.4, gives me two significant figures, 0.18 moles of gas. We don't know what the gas is, but it doesn't matter because, again, the beauty of Avogadro's law says that this relationship holds for any gas so long as that gas is at standard temperature and pressure. Now let's look into an example that actually does use the ideal gas law. What is the pressure of a 4 moles of methane in a 12.3 liter container at 25 degrees Celsius? So for this, we are going to need to use the ideal gas law. PV is equal to nRT. Our pressure value, we don't know. Our volume is 12.3 liters. We have 4.0 moles of gas. Our R value, since we're not told which pressure unit we're looking for, we can technically choose any one that we want. For the sake of argument here, I'm just going to choose 62.36 liters times torr divided by moles times Kelvin. And then 25 degrees Celsius is 298 Kelvin. So I need to get pressure by itself. So I'm going to divide each side by 12.3 liters. And if I set up my algebra correctly, my 12.3 liters cancels on this side. And all of my other units should cancel other than my pressure unit of torr, which is what we're looking for. My liters cancel because I've got liters in the universal gas constant in the numerator and liters down here in the denominator. I've got moles in the denominator of the universal gas constant and the numerator of my fraction. I've got Kelvin in the numerator of the fraction and in the denominator of the gas constant. So all that's left as far as units are concerned are torr. So 4.0 times 62.36 times 298 divided by 12.3, and two significant figures because of the moles. I'm going to get a pressure unit here. Pressure is equal to 6,000 torr, which, to be more precise, with our significant figures, we should put that in scientific notation. 6.0 times 10 to the third torr. Now, like I said, you could have done this in atmospheres. You could have done this a number of different ways. This was just the way to do it. That was using torr or millimeters of mercury. You just need to switch out the gas constant to do it in atmospheres. Use 0.08206 liter atmospheres per mole Kelvin if you wanted atmospheres here. The last example we're going to look at is a little bit different. Instead of using the ideal gas law just to figure out a parameter, we're going to actually use it to solve a problem. And you actually will do a problem like this in lab somewhere along the line here. You have a mass of a gas, 0.281 grams of a sample. You know how much space it takes up. You know what temperature you collected it at. You know the pressure that you collected it at. The question is calculate the molar mass. Now, to do a molar mass, you need a mass of gas and the number of moles of that gas. Well, the mass of gas we already have, 0.281 grams. It's a matter of figuring out the number of moles. And that's where the ideal gas law comes in. PV is equal to nRT. Well, in this case, we're trying to find N, so we're going to do a little bit of maneuvering. We're going to divide each side by RT to get N by itself. And so rearranged, PV over RT is going to be equal to N. And so that's where we're going to input our values to try to get them to work here to solve the rest of this. So our pressure is 754 torr. Our volume is 127 milliliters. We need to turn that into liters. So 127 divided by 1,000 is 0.127 liters divided by R. Since our pressure is in torr, we need to use 62.36 liters times torr divided by moles times Kelvin. And our temperature, 98 degrees Celsius, 98 plus 273 gives us 371 Kelvin. And so, once again, checking to make sure everything kind of cancels out. Torr cancel, liters cancel. I've got Kelvin in the numerator of this denominator and Kelvin in the denominator of this denominator. So those cancel out as well. What I'm left with as far as units is 1 over moles. You may remember that the reciprocal of a reciprocal is just what we had in that denominator as itself. So that means that we're going to end up with moles as our unit in total. So all of this gives us N. And if we do the calculations, 754 multiplied by 0.127 divided by 62.36 divided by 371, we get to three significant figures, 0.00414 moles of this gas. The molar mass of the gas then, we have 0.281 grams of this gas. We have 0.00414 moles of this gas. So putting that all together now, 0.281 divided by 0.00414, we get to three significant figures, 67.9 grams per mole as our molar mass. And so this is an example of one of the ways that we can manipulate the ideal gas law to help us to solve real problems in a laboratory situation. Like figuring out what the molar mass of an unknown gas is to help us to characterize that gas. So our next set of videos are going to be in a similar kind of vein to this, where we're going to start using the ideal gas law to solve other kinds of laboratory-based problems, looking at things like density of gases, molar masses of gases from experimental data, or even using gas phase stoichiometry and the ideal gas law to help us to do reactions that involve gases, whereas before we had to weigh them. So until then, have a good day.